So I guess people will show up, trickle in slowly, and we can get started. So this is one of the rare occasions where we have an opportunity to listen to each other rather than to an external visitor or a talk, and that we often find much more informative because people can talk about work in progress and also some recent unexpected results that they got that they haven't publicized. So maybe, so the way I wanted to organize it is that we go around the table, around the room, and people are welcome to mention very briefly some things that are exciting and that they work on or worked on over the past, let's say, 6 months related to black holes. And it could be in the form of a tweet, basically just saying, you know, I worked on this interesting aspect, and that's, you know, what I found. And then if there are questions, we can elaborate on that, so we can make it a discussion. But we can start with a tweet. So let me set the stage. I'll mention a few papers that I was working on, and then we can continue around the table. So as an example, we together with Manasvi Lingam and John Forbes, we consider the effect that the black holes may have on the possibility of life on planets in their vicinity. So the question is, when you have a quasar activity, that could sterilize planets in the vicinity of the black hole, and how much of an influence do black holes have on the habitability of planets? And so we actually calculated the impact of the radiation in the centers of galaxies and found how far out life could survive, how far out can an atmosphere still survive on a planet given the X-ray illumination. For example, in the context of Sagittarius A star in our own galaxy, it turns out that you can lose an atmosphere of a planet if you're too close in the inner tens of parsecs. So that's an example for a recent paper. Another one has to do with the highest redshift that we expect to detect gravitational wave sources. So LIGO detected sources out of redshift 4 to 1, and in principle there could be sources all the way back to when the first stars formed. And the question is, what's the highest redshift that we expect to see a gravitational wave source within the observable universe? It turns out to be redshift of 40. If you see anything beyond redshift 40, it means that standard cosmology has a problem. And that's because given the Gaussian nature of density perturbations, there was basically no structure. There were no stars to make gravitational wave sources prior to redshift 40. So if future experiments detect gravitational waves above redshift 40, then standard cosmology is in trouble. It's an interesting conclusion.
Is that the version?
No, it's the fact that there are no stars before that.
But you wouldn't expect initial perturbation to make some gravitational waves?
No, so the thing is, in the standard cosmology, there are no collapses prior to that redshift. So you basically have no objects. You just have linear density. You have small perturbations in the density that haven't collapsed yet to make bound objects. Okay, before redshift 40. And that's and if you sort of
weren't the things that ISEP 2 were hoping to have seen?
No, but these are
below redshift 40.
These are small density perturbations. So what the microwave background gives 10 to the minus 5 or so density fluctuations. You can't make stars out of that. You need these perturbations to grow and eventually reach all the unity, and then you get a collapse of the galaxy that makes stars. So this is the root mean square amplitude of all the 10 to the minus 5. You can ask, okay, but are there rare regions where the amplitude could be much larger? And the answer is because of the Gaussian nature of perturbations from inflation. It's exponentially suppressed. I mean, an amplitude larger than the mean is exponentially suppressed. And so that gives a very sharp cutoff above redshift 40, exponentially sharp, for expecting no sources beyond that redshift, which is an interesting point.
But you don't consider the time it takes after.
So I'm saying this is an upper. I mean, if you include the time, then it could be even lower. Okay. Okay, so but it can't be higher than redshift 40.
There's another question of how do you determine the redshift
Of a source.
Yeah.
Well, that's based on the amplitude, the frequency. So just like we do right now without an electromagnetic counterpart, if there is an electromagnetic counterpart, it's much easier. But I should say the easiest way to allow that to be violated is if you have non-Gaussianity, like some process in the early universe that produced fluctuations that are not Gaussian, they are not distributed like a Gaussian in terms of probability. So if you have a phase transition that makes a very big amplitude on some particular scale, then. But anyway, this is just a tidbit. A couple of papers. There were others, but I will not mention them. So let's go around the table.
So one thing I've been working on lately with Avi has been trying to see if it's possible to have phase transitions in nuclear matter when you have a neutron star merger. So it's believed that the QCD phase diagram has a phase transition at 0 temperature at several times the saturation density, the nuclear saturation density, which is reached approximately in the core of neutron stars. So if you heat that system up, if you're slightly below the phase transition in terms of density and you heat it up some tens of MeV, you would expect it to actually pass through the phase transition. And so we've looked at, together with a couple colleagues, we've looked at holographic models of the equation of state at high temperature and high density and matched that onto nuclear equations of state, and found that we can get phase transitions that occur at temperatures that are reached all the time in simulations of neutron stars, temperatures on the order of 10 or 20 MeV or so. So that's one thing. Another thing I've been working on, which has been an ongoing project for probably the last year or so, has been trying to come up with a new way to do numerical relativity, which will be much more economical, something that will hopefully run on my desktop computer.
How about an app on an iPhone?
What's that? Nobody would buy it.
Well, we would buy it. There might be a market for it.
How much? $1?
That's right.
It depends. If people start using gravitational waves for communication, they would need this software.
That's right.
Ramesh.
Yeah, so my group has been pushing ahead with these simulations of black hole accretion, and to a large extent that's kind of stimulated by all the activity with the EHT here. At least what I'm hoping is the EHT, apart from seeing this gravitational signature, the shadow of the black hole, etc., it will also tell us something about accretion. And in particular, I am looking forward to kind of very crude information from the EHT on what kind of radiation comes from the accretion disk versus whatever comes from the jet. Because most of these systems have got both accreting gas and also ejected material, both of which is expected to radiate, but the conditions are very different. The disk is a denser, relatively lower magnetized region. The jet is a very low density but highly magnetized region. And we imagine that the radiation processes will be quite different in these two regions. We want to reproduce that in the simulations. We can do simulations very nicely. We can take the Kerr metric, we can simulate the motion of gas, magnetic field, etc. But radiation is more complicated because radiation depends on what the particles are doing, how they are heated, what energy distribution do they take, is it thermal or is it non-thermal, does it have a power law distribution? We don't have a clue on any of these things, mainly because we don't have a detailed understanding of the plasma physics going on in an accretion disk, how particles are heated. So the program that we have been kind of pushing, and this is being pushed by my students obviously, and Michael Rowan here, he's doing some interesting plasma physics work. Andrew Shale, who is not here, he's off already on Thanksgiving, Yeah, these guys leave on Monday itself now, it turns out. They used to leave on Wednesday of Thanksgiving week, but now they're gone for a whole week. But, so he's taken the code which simulates our accretion disks, and he has put extra features where you can now follow in each parcel of fluid what the electrons are doing distinct from the ions. So the electrons are what we are interested in. They produce the radiation. So he's got a code that can actually follow a whole distribution of electrons in each cell, follow it as it moves along with the magnetic field, etc. And we can then compute radiation from this. But he's missing one key input, namely, in each cell, as you produce heat through all this accretion physics, how is that heat manifested? What kind of distribution does it put into the electrons? And this is plasma physics issue. So the hope we are having is that plasma physics simulations will tell us how to heat our particles, and then Andrew can put that prescription into the simulation and run it, and then we will calculate the radiation. Now we'll see what we see from the simulation. Meanwhile, the EHT will see what it sees. And the hope is that we can, by comparison with real data, kind of fine-tune our understanding of how particles are heated and how it differs between the accretion disk and the jet. There's a big program. This is what we are hoping to
There
achieve.
are two possibilities. Either the data will go along with the theory, or it will disagree with it. So if it disagrees, how do you fix it?
Well, the thing is, plasma physics is such a complicated
And you always have knobs.
field. I suspect there will be knobs. You know, we are trying to do all of this as 100% a priori as possible, without too many knobs. But you talk to a plasma physicist, they will tell you, oh, there are a zillion instabilities and this and that and all that. So yeah, so I don't know where this will go. But this is what needs to be done. You know, I think we've gone too long with just adjustable knobs. We need to get first principles
I
calculated.
had the impression that with Sag A star, that there wasn't much of an accretion disk, and that the
Something
most
is
of the
producing
emissions.
radiation.
Well, I get a mysterious answer every time I
Yeah?
ask the question where it's going. But I had the impression there was some kind of magnetosphere plasma around or
Yeah,
something.
yeah,
that was-
that's what I call the accretion disk.
Well, I thought the accretion disk was like something
No.
within 10 degrees.
No,
So
no,
you're
no.
just defining everything to be the accretion disk.
No, whatever goes in is the accretion disk, what goes out is the jet.
What goes out is the jet.
Ramesh?
And
please.
then M87 that has a very powerful jet, right? Isn't that going to dominate most of the image from?
For M87, we suspect the disk would be hard to see. Mostly will be dominated by the jet. But for Sagittarius A star, it's still an open question whether we're going to see the disk or the jet or both.
Isn't there a function of wavelength? And for M87, the disk may dominate the longer wavelengths.
Yeah, it may, but we have only the EHT data to look forward to. So
I was thinking we could tease it out by doing multi-wavelength.
that would be hard. You won't have the angular resolution, let us just say. You're the only one who's going to give us the angular resolution.
Ramesh,
And it only works at 230 gigahertz, maybe at 345 in the future. Yeah. Yeah. So Andy, yeah, that is the disk. All of these systems, what we call the disk is this. Look at the movies. They're big fat fellows that just kind of accrete over a big solid angle, and then the jet or whatever comes out over a fairly
What
narrow.
about the
solid.
corona?
You can call it what you want. Okay.
I'm trying
I-
to understand what you're saying.
I
Your
call it.
corona, I hear jet.
I have my own name for it, but you don't want all the jargon.
Okay, so the jet is everything that's going in, and the jet is everything coming out, and the accretion disk is everything going
At
in.
a very simple level, yes.
And what is the corona doing?
That is the corona, the disk.
The corona is going in.
Yeah. In this picture, yes.
Is it the region in between? Is the outer part of the jet?
These are names, right? I don't care
I'm
what
not
you
trying to
Not everybody would
Yeah.
agree with this nomenclature.
Yeah, so maybe you're trying to remember from Mislav's talk. He had Corona and Jet. He's talking about a completely different system. The systems we are talking about don't behave like your mental picture of an accretion disk.
Okay, so I should think of something like with a 30-degree opening angle? Is that
Or
what you're
larger.
imagining? Or larger, just
Or
kind
larger,
of.
yeah.
And what is going in?
it is gas and magnetic field and
Where does this
electrons
stuff come from?
and whatever is
Got it.
accreting from the exterior of the black hole.
Is there, you mean just
There's
random
amount of
interstellar dots?
Right. That's how it is in most of these galactic nuclei. They get gas from the surroundings. Some of it comes close to the black hole, goes into orbit, and falls into the black hole.
Ramesh, didn't you also have a hobby trying to look for signatures of naked singularities? Or is that not on the front burner?
I'm interested in lots of different things, but I thought I'd tell you about this
Sure,
thing.
but any news on that front?
The news is, there's nothing more to add. There are these solutions, but people will tell you that all the solutions that people have found are spherically symmetric and therefore don't count. It would be really nice to see non-axisymmetric or even axisymmetric but non-spherical naked singularity solution. Such things don't exist, they're just too hard to find. There's nothing more to add to that. Yeah.
Okay, so nothing new.
Yeah. Right.
Work in progress.
Wait, J greater than M Kerr must be axisymmetric.
But we don't know how to make that, right?
Yeah.
Yeah. Whereas the spherically symmetric ones, you can at least set up some initial conditions which will produce the naked singularity, but they will be highly symmetric initial conditions. That is their problem. Yeah.
Okay, we move on to Eric.
Well, I was also working on some accretion problems, which would be applicable to either black holes or massive stars. But anyway, this conversation that you were having about what you call things reminded me of another conversation I was having with people in star formation. They were saying, well, the infall is the material that's flowing onto the disk, and accretion is the thing that goes from the disk onto the star. And then I said, well, that thing that you're making around a massive star is not a disk because it's big and it's self-gravitating. And then finally said, but now look, you've reserved all the words in the English language for specific. So if you have something that's new and doesn't fit in, there's no words left that you can use. Anyway, so the problem that I was working on with Kenny was at the University of St. Andrews, and so we're starting. We want to get to a numerical solution of accretion and outflow with rotation, and right now we're working on a spherically symmetric solution. So we start off with a Bondi accretion flow, which is what the astronomers call a flow that just has the gravity of the point source in it. So you ignore the self-gravity of the gas. And then there's a simple analytic solution from the Euler equation. And then if one imagines that the central source is an ionizing source and that there's an ionization front, then again, you can work out an analytic solution for the flow coming in initially as a neutral or molecular accretion flow and going through the ionization front and then proceeding on in toward the source. So we put this on the three-dimensional numerical code, but the solution isn't stable, and so they're saying, well, your solution is not stable, and I said, no, of course it's stable. I checked it on the second derivatives. Your code's not working, and so we're now trying to resolve this situation. So it seems like it should be stable because when the flow goes through the ionization front, the gas is compressed. So the ionized inner part is a higher density than the outer part, so you wouldn't get Rayleigh-Taylor instabilities, which you often see suggested in the literature that there would be Rayleigh-Taylor instabilities in this sort of Bondi accretion flow phase, but that's not correct. So, but there could be something else. But anyway, we're working on that, and then if we get the spherical flow to work, we can go on to it's a 3D code, so we can go on to put it in the rotation, and then what one would like to see is the breakout of the ionized jet from. You'd start with a rotating accretion flow, and that flows onto the central object, whatever it is. And as the ionizing radiation increases, then you get to that bonding Parker critical point, and then the ionized gas is no longer bound to the point source, and it will break out, presumably in the path of least resistance, which is out the poles of the.
So, Eric, this Bondi accretion, you say you're doing it in 3D?
Yep.
Okay, and you said the density increases through the ionization front.
Yep.
What does the entropy do? Is it stable or unstable profile?
I don't know.
I would guess that it is unstable.
Might be, you think?
I think your ionized, but your 3D code would find the resulting convection. If you didn't see it, then it means it was stable.
Yeah, that's a good suggestion. Yeah. Anyway,
Something to
okay,
check,
yeah,
yeah.
that's what we're working on. So.
Good. Very
Sounds
good.
great. Why don't we finish going around this table and then we'll go to the periphery? So,
Okay. So I'm still stuck on this problem of gravitational perturbations of higher dimensional Schwarzschild. So it's a very classical problem for a mathematician. These things are governed by, they sort of split into different sectors, and they're each governed by sort of master wave equations. And when you go to higher dimensional settings, the potentials for these wave equations, you can think about them as Schrodinger type equations with really nasty potentials as you go to higher and higher dimensions. Above dimension 4, for one of these equations, there seems to be an obstruction. I was in Hong Kong for a month trying to work on the resolution of this, trying to prove that there was some estimate, and actually what we got at the end of it was that such an estimate could not possibly exist. So you want to prove that these things disperse or decay, the gravitational perturbations do. So each of these equations needs to show dispersive behavior. And what this is saying, the non-existence of this estimate is saying there's some obstruction to the normal chain of boxes you want to check on the way to proving this dispersion. So it's not to say the fact that this estimate cannot possibly exist, it's not to say that there cannot possibly be dispersion, it's just that you need some new way of looking at this. And the current way that we're going about it, or the current idea is that in the classical Schwarzschildian case, there's a transformation that maps between, there's some duality where you map between two of these different equations. So somehow the Reggie-Wheeler equation becomes the Cirilli equation, and the Cirilli equation becomes the Reggie-Wheeler. So this is some classical result under Sekars. And the question is, so only one of these three equations has such a bad potential. The question is, can we find a way to transform it to something, a new Schrodinger equation with a new potential? Estimate that thing and then pull back to the original. So that's sort of what's done with the Tucholsky equation in the math GR literature. So it's sort of a question of whether that's possible in this setting.
and you found the Hong Kong background inspiring?
I was just working all the time, actually.
So is it translation?
It could have been Boston.
Progress is independent where you are?
No, I think actually we made much better progress there because I was worked to the bone when I was there. So just meetings
So maybe
all
going
the
to
time.
space would be better. Okay, let's
So,
move on.
are you saying it's still an open question whether Schwarzschild is stable in these
Informal.
arguments?
I don't think so. I mean, I think that to physicists' satisfaction it'd be fine. So the original people that took this problem on are these two Japanese fellows named Kodama and Ishibashi, and I think they're actually pretty well-known people. So they're pretty serious people. And they took this question on and just proved that the thing was sort of mode stable. So then the question is, could we prove this pedantic thing of going beyond mode stability? So I think, you can sleep at night about that.
Yeah, I was so worried, yeah. But can Paul just simulate and show that it is stable?
I'd be more interested in whether, well, that also would really...
Is that a question for me?
Yeah, no, I'm asking Jordan whether that would be considered proof of stability.
Oh, you mean numerical?
Yeah, numerical,
But then
yeah.
there is some precision, so you never know.
And somebody can say, well, if I started off with different initial conditions, maybe,
No, you can start it, you kind of punch it.
Yeah, but you could do it for some finite set of initial data, and then a mathematician will say, well, you didn't do everything.
No, I just want to know, when are you satisfied?
No, I mean, there's simply no reasoning with some people, and
Yeah.
people like me, so sometimes Paul could never...
He'll never satisfy you by running a simulation, okay.
So the bottom line is physicists sleep better than mathematicians.
Yeah.
Laura.
Yeah, okay, so I guess I'm still interested in understanding better symmetries that are arising near black hole horizons. And okay, I've been talking about that again yesterday, so I don't want to bother people again with that. But I guess what I would like to understand is how all these symmetries that arise can be related to the BMS symmetries, and understand all these towers of infinity that arise are very interesting and rich, and maybe understand better what happened in the extremal case that we were talking about yesterday, because somehow it's very different to extremal one. Right. So, and I guess with Andy we're working on something that is still is related to BMS, since it's in this context of the sub-theorems, and we are looking at amplitudes in flat space, and how we are looking at some conformal theoretical properties of this amplitude. So how we can rewrite amplitude in flat space has, say, endpoint functions in the CFT, so it's more like a flat holography context. But I guess it's still work in progress. We have to understand what's going on. Yeah.
And this relates to the ultimate quest to find a solution to the information paradox, or not?
Oh.
Will it, or it's part of the problem, or not?
Yeah.
No?
All problems in physics relate to solving the information paradox.
So this is not necessary.
Not necessarily, but yeah, if we understand this better, then of course
Could
we
help.
will share it. So,
Can you tell us about any new result from LIGO that we haven't heard about?
thank you.
So I've been writing out a paper on end-to-end simulation of how well LIGO can measure the Hubble constant. So there are several different approaches, but it always starts with LIGO measure the source luminosity distance, and we need some way to figure out the redshift. Either we detect the counterpart, or we don't have the counterpart, but we use all the galaxies surrounding the region, and then consider the redshift of all the galaxies. So there are essentially these two approaches. So I try to investigate them for different kind of source for binary neutron
Do you know
stars.
which galaxy it's in?
So if you have an EM counterpart, then you will look around, see if there's a host galaxy that's close by. So that can be your host. So that is one approach. If not, then you consider all the galaxies in the regions.
But also the distance, I mean, the gravitational wave data tells you something about the distance of redshift, and so you are slicing the universe in a narrow shell. You're looking just in galaxies within a shell.
It's more like a volume of some shape so that you can cut it off. You assume some H0 prior so that you can cut off. So yeah, just finishing that up so that we can make a prediction for if we have, given now we have binary neutron star, we kind of know the rate and how well we can do it in next year, next few years, and also some people ask for binary black holes, we expect a lot more detections of binary black holes. So how well can we do H0 measurement if they don't have counterpart or if they have counterpart? So just kind of answer all that question in one paper. And
Is it true that all the future events will be public immediately, or not?
we're discussing.
You're discussing that?
Yeah, it's
And is it leaning towards yes or no?
no leaning. We're just trying to write down all the proposal and all the consideration and start the discussion.
Well, it depends how many Nobel Prizes.
That's right.
One is in the bag, and then the second perhaps for the neutron star magic in the future. But there could be more. You know? Just like the microwave Bergman produced multiple Nobel Prizes. Misla.
I'm glad Ramesh brought up structure of accretion disks and then jets and coronae, because that's something I'm now working on with another BHI speaker, Martin Elvis, who presented part of this. So the idea is to not consider all the physics. Ramesh is taking care of that. Just to simplify.
Not for your systems.
Yes, not the same systems, but the idea behind this work is to understand how things scale with mass and accretion rate. So eventually it will we will get to low accretion systems that Ramesh is studying. The idea is that so the corona, which is what emits the X-rays, has to be some very hot plasma somewhere very close to the black hole, and all we really know about it is that it's very compact. The question is why and how and what does that represent? So if it is a compact, hot region with electrons and protons, but electrons are what matters, perhaps positrons, it's kept together probably by some kind of magnetic field. So constraining the size and the luminosity of these coronae tells you something about the strength of the field required to maintain it. And so there's a number of different probes of this region available that from methods that did not communicate between each other. And one is from broadband spectroscopy, one is from microlensing of quasars at high redshift, and then there's population studies which tell you what is the average offset between supply of photons, which is the accretion disk, and the corona, which is observable in X-rays. So combining all these can get us where we want in terms of how much magnetic field is required to power this corona and how that scales with black hole mass and accretion rate. And that may be an input to models to try to reproduce the details of that once we have the basics figured out.
Now, corona also are found in stars, right? The sun has a corona.
That's where the name.
And is that well understood or not?
I
Because
think
the sun is next to us, we can look at it.
yes, I think a lot more is known, but then again, I think they run into this issue that we don't really understand plasma physics well.
So if we don't understand the sun, can you hope to understand the quasar?
Yeah, I mean, otherwise we would all be studying the sun.
Actually, how big is the sun's corona?
Oh, it's a few times the radius of the sun. I mean,
The photospheric radius.
sorry?
It's a few times the photospheric radius.
Yeah. And by the way, over the summer I visited Hawaii. On one of the mountains there, they're building a solar observatory that cost about $300 million to NSF, taxpayers' money. They're about to put the glass and everything as we speak. And it will start operation in 2019. And one thing they were complaining about is that they don't get enough photons from the sun. I mean, most of the setup, the construction has to do with cooling because they focus the sunlight on a small, region, and you have to cool that region. But still, they don't have enough photons because they spread the photons across very fine beams in frequency or wavelength. So they look at spectroscopy of lines and how they change in time on short time scales, and so they struggle with the number of photons they have available within a narrow beam of wavelengths and over a short time. I told them that it's a problem with human nature, that we always go to the limit of what our instruments give us, irrespective. I mean, can you complain about how many photons you get from the sun?
We're never satisfied in whatever situation it is.
So they are trying, exactly, so they will study the corona as well, and presumably we'll learn more about it.
And do we know that it's force-free?
In the sun, you mean?
Yeah.
I'm not sure. Does anyone know?
It's a good approximation. It's magnetically dominated and it's pretty conductive. So certainly the models that people develop start with the kind of force-free assumption.
And do we know the moments of the magnetic field, like how strong the multiple moments are?
Yeah.
Yeah, because they make actually images.
But the thing is, the corona is presumably heated by loops of magnetic fields reconnecting and releasing energetic particles, and it's very complicated plasma
Yeah,
physics.
it's not a simple dipolar field. It's got all this extra stuff,
bubbles
coming up and loops and
Did you watch the eclipse?
No.
No, because then you could have seen those bubbles. You can watch it on the internet.
Safer.
You can also
Actually,
see the corona.
The
Sorry.
corona was really visible
Yeah.
during the eclipse.
But you want to put your black hole solution on the sun? Is that
I want to get an analytic solution.
analytic
for the
magnetospheric
force field of the
solution?
sun.
Yeah. The solar neck.
Yeah, I mean, it sounds like we know that it's force-free and we know the multiple
Well,
moments.
you should look at that. Maybe
Yeah.
I mean, never assume that astronomers were smart enough to find the right solution. So you might find it
Yeah.
yourself.
In fact, you can assume that astronomers are not smart enough to find the right solution. So, yeah.
Yeah.
There's certainly
You
room
would be
for
surprised
physics.
how many areas in astronomy could have been solved and were not, from experience. Anyway, let's continue going around. So we'll start with you and then. Go ahead.
So probably the most relevant thing, I guess I
Just mention your name.
Oh yeah, my name is David, and most relevant thing related to I suppose black holes has actually been something my colleagues and I have been doing. We've been looking at the Kerr-CFT correspondence. It actually it's been a on and off going process that we've been doing. Actually, it relates to a paper that was published by Andy not too long ago about the Kerr-CFT. What we did is, one of my colleagues, he has his own paper, he actually has data from the gravitational side, and we want to see how, and in Andrew's paper it actually talks about how there would be a match between the conformal field theory side and the gravity side. We actually did find for positive quasi-normal modes, we found a beautiful match, actually matched perfectly, just like the paper said. However, with the negative modes, unfortunately, we did not find such a match.
How do you explain that?
Huh?
How do you explain the difference?
That's something we're still working on. We're still trying to figure that out, exactly what's going on, particularly with the negative modes. Really are dissecting the equations bit by bit now, and but we really are hoping to find out more about them, more about the correspondence as a whole, as well as about the behavior of the negative modes in the Kerr-CFT.
So this correspondence was a conjecture, just like the ADS-CFT, or was
No.
it was proven?
Yes.
So
Okay, so much confusion about this. So it isn't a conjecture that when a black hole becomes extreme, that it gets an infinite dimensional conformal symmetry. That follows from the Einstein equation. It's a subtle analysis. It's like the kind of analysis that BMS does, but it's true. That's not a conjecture, and it's been used to, the symmetry has been used to compute all kinds of things, gravitational waveforms, all kinds of things that would be impossible to compute if you didn't know about the symmetry. So it's a computationally very powerful and effective symmetry. The conjecture, which is where it all started, is that, following the model of string theory, that the black hole microstates are in a quantum representation of this symmetry, and that we can use that to compute the Bekenstein-Hawking degeneracy. And if you make that conjecture, you get the area wall. But we don't know what this conformal field there is. That's quantum gravity. You can't, anything which has quantum gravity in the same sentence is a conjecture because, so that part of it, the connection of Kerr-CFT to the information problem and to the Bekenstein-Hawking entropy and all the quantum puzzles and everything, that part involves a conjecture. But the connection to astrophysical measurements, the kind of thing Alex was talking about, that's just learning clever new. In the end, it's just learning clever new methods and new ways of organizing and thinking about the Einstein equation.
So these negative modes, the fact that they don't abide by the,
It has to work.
Does it have implications for the conjecture?
Well, no, because he's doing classical physics, so somehow there has to be some way of looking at it.
So you think it will be resolved?
I think it will be resolved,
okay.
yeah.
Okay, so it's not really a problem.
Well,
No, I mean,
I don't want to.
We're looking-
something will happen. There'll be some way of making
either
sense
it's
of it.
conjecture or
we
it's
thought-
proven.
yeah.
If it's proven, then there is no way that he can get something else, right?
Yeah, or maybe it's in the wrong regime. Who knows what? I'm not saying that.
Right now, we feel we really just looked at things at late times. We feel we actually study things at early times. We may be able to get a better understanding of what's going on with the negative modes. Actually spoke to one of your co-authors. I made exchanges with Oculus about this.
Yeah.
Trying to resolve things. He was actually a bit shocked in the paper that there wasn't a match for the negative modes. He figured it would be the same, but then he explained that just to simplify some of the final equations in the paper, that you guys only focused on positive modes.
Yeah, I mean, another thing to say here is, I mean, when we first discovered the symmetry, we discovered, okay, here's the symmetry, we showed the symmetry, that's it, problem solved, you know? Then a little later, we started thinking, well, what are you going to see when you look at it at the sky?
Right.
And that gets insanely complicated. If you ask a physical, you know, if you formulate it in one basis, it all looks very simple. But then when you ask, you know, what is Shep going to see? What is Ramesh going to see? You know, like then you have to know what a corona is, and you have to know, you know what accretion
And I'm not telling you that. Yeah.
And you're not telling me, and you know, and then all of a sudden, not only does it get insanely complicated, but you realize that you didn't understand it as well as you thought you did. You know, you didn't understand. It goes back into our you know, our understanding of it. Yeah.
That's good. Andy, would you like to mention some other things that you're excited about?
Yeah. So
Tell us how quantum gravity works.
that I can't do, but I can tell you the project I'm working on now. So, like 20 years ago, Vafa and I used string theory to some special techniques in string theory to count microstates of a black hole, and one of the tricks that we used was we related a universal formula in general relativity, the Bekenstein-Hawking area entropy law, to a universal formula in two-dimensional conformal field theory, something called the Carty formula. And at that time, it seemed like an accident that we were relating these two things. And I spent a lot of time trying to count microstates and examples where it wasn't the Carty formula. Somehow I didn't think they were related. But as the years have gone by, every successful counting has been you relate the universal formula in general relativity to a universal formula in two-dimensional. So it's starting to look to me like that's the general lesson. Okay, anyway, that's my working hypothesis now. So we have recently understood, you know, in the last few years there's been great progress in understanding. So diffeomorphisms in general relativity, we're told that they map physical configurations into equivalent physical configurations. That's almost their definition. But that is subtly wrong when the diffeomorphisms don't behave well at the boundary. This is what Bondi, Metzner, and Sachs discovered 50 years ago. But the meaning and the way to use their formula was not understood until two or 3 years ago. Now I think that story is fully nailed. But there's a story about how they act on the horizon, which is a story that many people have been grappling with, me and especially in collaboration with Malcolm and Stephen Hawking, and now Malcolm's student Sasha Ako. So where do you have a conformal symmetry for a regular black hole? We know we have one for an extreme curve, but what about for a regular black hole? Well, there is a very mysterious one. So anybody who's played with these things know that if you solve the wave equation in a generic curve, not necessarily an extreme one, you divide the near region and the far region and you solve the wave equation in the near region, and anybody who's done this will remember, I mean, it's in all the textbooks, that the near region solutions are always hypergeometric functions. And hypergeometric functions are representations of SL2R, which are the conformal group. So somehow the conformal group is rearing its little head there. In fact, it works out to be two copies of the conformal group. And we have been studying how that, we identified what that, there's a canonical way to identify how that group acts as and its infinite dimensional extension to the Virasoro group, how it acts on the horizon of a generic black hole. And now we want to see if that symmetry group, there's a symmetry group that acts non-trivially on the black hole, even though it's a diffeomorphism, and we're hoping that that symmetry group will be the key. Understanding that symmetry group will be the key to understanding the microstates in general.
So, Andy.
Yeah.
Laura's model, which she described for us yesterday,
Yeah.
does go to general, I mean, non-extremal black holes, right? She seems to be able to do at least the BMS kind of analysis.
In 2+1 or?
No, 3+1. 3+1, I mean, she's got a framework where you can do the extremal as a special case, but the general case is what you described, right?
Mhm.
So I'm just trying to understand.
Yeah, I guess what Andy's looking for is a central extension in the algebra, and we get a central-less algebra. So we didn't have, the central charge that is the key ingredient in the Cardi formula.
Uh-huh.
We didn't have this quantity, and I think that's what Andy's looking for.
Okay.
Yeah, and if you have this central charge, then you can use it in the Cardi formula and recover the entropy from a purely CFT computation.
Okay.
And that's, I guess, why we didn't find this.
Okay.
Right, so there's a consistency check on our whole story, which is a number that we have to compute, which in principle is completely well-defined. And when we first boiled it down to computing this one number, when was that, Malcolm? September?
September.
It was, okay, we'll have this in a day or two. Something about Kerr. Calculations could go on for a long, long time without becoming impossible.
Kerr calculations are not so easy.
But you are still here, so
Yeah.
there is plenty of time. Andy, what you said before reminded me of this quote by Yogi Berra, that in theory and observations are the same. Observationally, they are different. Anyway, we move on.
So I just actually have a quick question. Since you mentioned Vafa, maybe this would be the best question to ask him, but this is kind of embarrassing since string theory is my primary interest, but what does the F in F theory actually stand for?
It's the father.
Father? I'm guessing father. If M is probably mother
M
of
is
theories,
mother and
F is...
father.
Okay.
Like,
Simple as that.
Yeah.
Okay.
There are other possibilities.
Ramesh,
Well, I'm not sure.
Ramesh, you noticed that the string theorists kept silent. You were too naive to speak up. Anyway,
I mean, yeah, unless the N is really an upside down W for Witten.
Yeah. Right.
we move on.
I'm Michael Jansen. I'm a visiting student from the Netherlands, actually visiting MIT Haystack Observatory, but I come down here every Tuesday, and I work on the Event Horizon Telescope project on the data calibration. So it's very technical, and I don't think I should go. Sorry?
Only 3 + 1 dimensions.
Yes.
Nice. So I guess you are doing part of your PhD.
Yeah.
Here.
Well, Mikhail is being too modest. He's kind of leading some of the a priori calibrations, so he's turning the data that come out of the VLBI correlator, which are just numbers, into brightness on the sky. and that turns out to be a very complicated problem because you have to know intimate details about all the telescopes.
And the university allows him to spend time here during his PhD.
I don't know how this works. We just
Me neither.
he's just he shows up. We give him sandwiches. He produces
It works,
numbers. You don't ask questions.
That's good. Okay, Rudy?
So I'm puzzled by how theoreticians are being so successful at ignoring the observations of Sagittarius A star. There are 3 observations now that are out there that the theoretical community would prefer not to talk about. To quote Ramesh Narayan, "I'm so tired about answering about G2. So there's first the problem, the G2 cloud. What went wrong with all of that? Then there's the problem of the magnetic field, which is observed by observing a pulsar that's just beyond the horizon, or just beyond in distance, the Sagittarius A star image. And the strong magnetic fields are indicated by the Faraday rotation that must occur associated with Sagittarius A star. And so there's no discussion of magnetic fields, even though the initial reports came along and were widely broadcasted as saying, gee, these magnetic fields that we're discussing and measuring are surprisingly strong. And everybody knows black holes have no hair, so it seems that it's highly desirable to ignore them. And then there's the third problem with observations of Sagittarius A star, and that is this picture from Ryan Tao et al. Of Sagittarius A star made with the Sophia forecast. That's the Boeing 747 with the telescope in the back end, and the principal result of that mission was this picture of...
What's the scale?
Sorry?
What's the scale, the physical?
Yes, the 1 parsec is about this big on this plot.
Okay.
So
Wait,
it's not the horizon side. One parsec is about this big.
1 parsec is a million...
I'm sorry.
Is a few million Schwarzschild.
Thank you.
A few million.
Okay.
Yeah.
Thanks, Avi. So, this picture is a culmination of that event, but the final report, which is in the form of that paper published by Ryan Lau, says that this enormous luminosity, which is the luminosity that is seen in all quasars at cosmological distances, is known from its spectrum to be either synchrotron radiation or Bremsstrahlung, but I say most likely synchrotron radiation because you can see how it is tied to the magnetic filaments that seem to terminate at the surface of the object. So I'm looking to magnetic solutions, that is, solutions where the compact object has an intrinsic magnetic field, and those exist and predict the structure that Ryan Lau said, we can just call this an asymmetric structure seen near to Sagittarius A star with no understanding. So that's what I'm listening for.
Thank you, Rudy.
Are these the solutions where the ergosphere goes all the way to infinity? What are they called, these solutions?
These are called MECO solutions, or the magnetic eternally collapsing object solutions. So that's an independent set of solutions
It's
of
a
the
non-black hole.
Einstein-Maxwell field equation.
It's not a black hole.
It's not a black hole.
Yeah. It's
Yes.
kind of an alternative.
An alternative to black hole theory, if you allow the possibility that quantum electrodynamics dominates the structure of the object and suppresses the collapse, the gravitational collapse. Okay, I've said enough.
Peter, you just entered. You didn't have a
Crossed
sandwich,
the continent.
and you crossed the line where we go around, so you have to speak now. Do you want to say? I mean, it basically a couple of minutes about the most exciting thing you've done over the past 6 months.
You walk right into Avi's rules of order.
Okay.
And you'll get a sandwich as a
In
reward.
Okay. Mainly I've been filming and working with Faraz on the working group in philosophy, and Ramesh and many others have been.
Any new insights from that group? There's something that you didn't expect when you entered the room.
Well, it's been very interesting. We've been mostly focusing on on singularities, and I think that the discussion has been really helpful and interesting, looking at different people's approaches to that.
Is it well defined? I guess the material, the reading material, implied that you can't define singularities, right?
Absolutely.
Right.
We still haven't figured
It's
out how to
very
define
slippery. And I just gave a talk, which I had worked hard on material, the sort of the analog, the philosophy of these analog models of black holes, which I've been a little dubious about, and I have some ideas about how to think about those. And then filming, which has been great with many of you. So.
Peter, when you say analog, these are these experiments?
Well, they're everything,
The
from
acoustic
quantum
experiments?
ones to ripple ones to bathtub vortices to.
But it's not really gravity that is being realized here, and so I mean any analogy. I mean, obviously will work with whatever quantum mechanical description you have.
Some of these are not quantum, actually. There are other things, but it's I sort of putting them in a series with the Maxwell era analog physical models of the ether, and then other kinds of material models, for instance, of the economy. They have these big machines that model with actual liquid flow, the British economy in the 1940s. So it's actually very funny.
And now it has a leak.
It's called the Moniac. Yeah.
They found a leak. Yeah.
So the leaking is the inflation. So the
Make one for Bitcoin.
anyway, so it's been very interesting to sort of think about these things systematically and what it is that people expect that they're getting at through this form of understanding. So I've done sort of a philosophical gloss on what Maxwell and Lodge and all these guys thought they were doing with these rubber band and wheel models.
By the way, also in astronomy, before numerical simulations were realized on computers, people tried to make realizations of n-body systems through shadowing experiments, where you, because in principle, you also have 1 over r squared kind of geometry, and trying to do like a primitive n-body simulation by measuring the amount of light that you have at different points, which implies the gravitational acceleration from a lot of vast light bulbs. That was the early form of simulations. In terms of your filming, did you get cooperation as you wished from all interviewees, or was that?
Yeah, pretty much. It's been recently. I've been filming the group with Stephen Hawking, Andy, Malcolm, and then EHT things, and continuing to follow those two. And then probably the most challenging part is actually the philosophy side, to figure out. And I've started to work with a graphic novelist to explore the sort of more tentative philosophical explorations of interpretations of black holes. There's a very good woman named Glenys Fawkes, who's a terrific graphic novelist, lives in Vermont, and I've started to send her to put together some of the things on philosophy and get her feedback. And so those are the 3 strands, sort of history and philosophy, information paradox, and EHT, sort of those are the 3 main lines.
Nice. And you were wise enough not to produce it with the Weinstein Company. How long is how long is the movie going to be?
About 80 minutes. It'll be a feature film.
Great. You deserve sandwich.
So I'm Alex, and I have 2 separate projects that I'm working on. One involves using these symmetries, this conformal symmetry of extreme black holes, the part of the Kerr-CFT correspondence which is proven, to make contact with the experiment, which, as Andy mentioned, is very hard. So a couple of weeks ago I gave a talk in which I presented our results that were published earlier this month for the optical appearance of one point source orbiting near a rapidly spinning black hole. And the result, if you recall, was that all the light came on this neckline, which is the vertical edge of the shadow. And that's kind of the Green's function version of the problem. That's one point source. And now I'm writing a follow-up, which I expect to be out by the end of the year, where we do the disk. And what's interesting is that actually that calculation is much easier because you sort of don't have to keep track of the details of where the source is. and we get a very nice, simple, universal answer, which takes the form of this hypergeometric function. That's as Andy mentioned, the hallmark of this conformal symmetry, and it's completely insensitive to the details of the disk. Yeah, and in that sense, it's a universal feature because we did a simple toy model where we just put a bunch of hotspots and you get an answer. We did an Optical Thorn model, we get basically the same answer. So the overall intensity along the line can change, but the relative height of the flux along this line, that result is universal and independent of the features of the disk.
And you include the Doppler effect in addition to the gravity.
Yeah, it's a GR calculation, completely GR calculation. So that's like basically a curve you can plot, and it tells you as a function of where the observer is, what elevation on the neckline they're looking at, and what redshift they're measuring as a precise analytic curve.
But is the shadow going to be just a line?
So the idea is that the shadow in general is vaguely circular, but at extremality it develops this vertical edge, and all the light that comes from the near horizon is constrained to come to
That's
appear
the
on this
light,
line.
but the shadow itself is the rest.
Is the rest.
So it's only so it's a one-sided moon crescent kind of.
Just inside the shadow.
Right. Well, yeah, it can be on both sides. So the light that comes straight out actually is within the shadow. The light that is reflected is, by the definition of the shadow, slightly outside. So there's light on sort of both sides of this vertical line segment, and the distance from the line is set by the deviation from externality.
So what happens is you look at it not edge on, because edge on is when you see it one side. But what if you look at it?
Right. So this is an analytic formula, which is hypergeometric function times a function which is a property of the observer. And if you go too far out of the plane, then this neckline closes. I mean, the shadow's vertical edge disappears if you're at an angle that is greater than about 30 degrees above the equatorial line. So there's an opening angle of about 30 degrees that you have to be in for this line to develop and to see it.
But what happens if you go outside that? You still see something.
Well,
so we haven't. I mean, I think that's an important problem. We haven't really studied it yet. So I mean, because
for M87,
exactly for M87. So what the conformal symmetry predicts for M87?
But one can do ray tracing and see that you get the answer.
Well, you could do ray tracing for anything, but ray tracing is very it breaks down. You see what happens is you get this infinitely long. So it's basically a critical phenomenon.
Well,
when a critical phenomena occurs, usually computer simulations break down unless they're prepared
unless you
for
use coordinates that somehow mitigate that, right?
Well,
it's not
as you get exponentially close to the symmetry point, you need exponentially more grid points.
No, but then you can, instead of a fixed grid, you can make coordinates that are exponentially close.
You could do that, but you can also solve it analytically in this.
Yeah, actually, if there are people in this room who know how to do this numerically, it'd be a great, I think.
Well, there are a lot of people who work on GR and ray tracing with CK, for example.
Yeah.
But is this too close
None
to
of these codes will work beyond 9, maybe 4 nines.
Well, but they were having trouble with the hotspot. They were having trouble above 0.7.
Okay.
Well, because they didn't optimize it, but maybe.
Well, one thing which I didn't really include in my talk, but in talking to Chet afterward, I think it's a relevant point to make. In this analytic calculation, you get these continuous tracks of images that move up and down the neckline. But the closer you are to extremality, the more independent photons are required to produce this continuous track. So what you see is a continuous image, but at certain time intervals, the photon that produces the image disappears, and whenever that happens, there's another photon with different winding numbers that magically appears at just the right time to keep the image continuous. And so, even for one continuous track, you actually have to keep track of like 10 different photons.
So in principle, you can get superluminal motion faster than light, even if the source is moving less than the speed of light. The image can move faster than light.
Oh, right, yeah, that's
on the image plane.
Yeah, I guess we haven't looked at it in principle.
That would be interesting. But the other thing is there is this theorem that people argue that the size of the shadow is almost independent of the spin, right? But that probably is not true at the limit, right?
You have to be at 99% of externality.
And the size of the shadow is roughly constant, independent of how close.
No, but analytically you can show that for Kerr, it has a certain width.
Right, but does it change significantly as you approach the extreme?
Well, it changes the shape. There's a formula for the shape that depends on the spin, but somehow I don't know what, the quadrupole moment, there was no dipole moment, you know, it's not much change as you expect, but I think there could be other dramatic signals like this one. That's just a statement about the shape of the shadow from backlighting. It has not, it's not a statement about the emissions from accretion disk or hotspot that is coming from inside the black hole. And those have a highly spin dependent characteristic. And there's other things too, like there's a maximum and a minimum redshift, which in this limit can be analytically given as square root of 3 and 1 over square root of 3. So if you have an iron line, you know, whatever 6.4, in fact we looked at, somebody saw one that wasn't quite right, but if you see even if you don't have a resolution, if you see a dot in the sky with a peak, it's 6.4 over the square root of 3, which is about what?
It's 3.6.
3.6
is your next challenge.
Yeah, if you see that, that's like a smoking gun for.
Apparently, there is an unexplained peak.
So many ways there are many, because it's a critical phenomenon. There'd be many ways that you might hope to see.
So Mislav has data at 3 keV, right? You can look at if there's any feature there.
The trouble is though, when you're looking at a disk kind of edge on, which has to be satisfied for now at least.
Or even up to 30 degrees above the equator.
Yeah, typically you would observe an AGN looking at the disk from high up, because the edge on there's other material flowing in that has a larger opening angle. So you can rarely get a glimpse of an accretion disk at such low inclination or high inclination, I guess.
Unless
Really? You don't
inefficient.
With Sag A star, if it's rotating,
that's
no reason to think it's rotating fast. But if it is rotating, wouldn't we expect it to be its axis to be nearly perpendicular to the line of sight?
But that's
It's a line of the galaxy. Yeah, it's a line of the galaxy.
But that's relatively inefficient, so you can look through the material that flows in. Mislav is looking at disks that are opaque.
This goes back to your question to me, Andy. Our galactic center is a different beast from the kinds of beasts that Mislav looks at. And I think the iron line is his kind of system.
Although you can, in principle, imagine it also.
You have to have high density to get
and low temperature.
Right.
So if you have clamps in a thick configuration.
But the other thing nice is about it, these critical points, is that this large number of parameters you have to put in, most of the parameters become irrelevant.
Right, of course.
And so you get much more robust theory independent
Alex?
predictions.
The other thing I wanted to mention, which I haven't really talked to you before, but I'd like to, I think some of you could really give me some interesting input. So for the last couple of years, I've been studying these force-free equations, and there's been a lot of interesting developments in the last few months, and in the stationary axisymmetric case, it turns out I've been able to reduce them to a linear equation, which you can completely solve. So in principle, that means you can completely, you should be able to write down an analytic expression for any stationary axisymmetric force-free field. And so I'd like to, now that there's this tool, the question is, what are the most interesting?
You have a hammer, you want to hit some nails.
Yeah,
so one possibility, there is pulsars are a very good environment.
Right, so I think the dipole pulsar and the sun are the obvious.
Sun is not axisymmetric.
It's not axisymmetric.
Well, probably zeroth order you could think of it axisymmetric. But all the interesting phenomena are the non-axisymmetric flares and bulges and stuff. Yeah, and pulsars typically they are tilted, so that's not so good. But you could do the aligned rotating neutron
pulsar.
star. Yeah.
And that's a textbook. I mean, there are discussions in the literature if you want indirectly.
Right.
So that would be a good place to start. And people try to solve the equations there. There is a guy named Anatoly Spitkovsky at Princeton that does numerical simulations. Andrei Gruzinov from NYU tries to get analytic solutions to this. These are people that worked on it for a couple of decades, and they're quite bright, but you might actually have something they don't have. It's useful.
Okay, so Michael, Ramesh already outlined this project earlier about providing for simulations of accretion disks on black holes. And so the part of this that I'm working on is the plasma physics. So this provides the subgrid resolution that's not available in MHD simulations. And so the first part of this project is that we've been studying like electron heating, proton heating, and the outflows of these like reconnection sites. And so the first project of this is it's available paper, like the final published paper is available online as of about 6 or 7 days ago. So if anyone's interested, you can find it online. So more recently, we've been looking at extensions of this first project and looking at different regions of the reconnection outflows. So studying electron heating and not just the direct outflow, but further downstream after everything's sort of thermalized. And so we're also interested in the mechanism of heating, so providing some more explanation rather than just the numbers. Numbers are useful, but it's also helpful to understand different mechanisms of the heating.
And so lessons from the solar corona are helpful in that regard, or not much?
Yeah, I think they are. There's been a lot of work in solar corona regime, but this is like a non-relativistic regime, and so it's a little bit different for when particles are relativistic.
Thanks. Shep, what have you been doing over the past 6 months? Other than
Yeah,
this
sure.
data on Sag A star?
Nothing. I'll just say two quick things. One is that we are working very hard on the EHT data. A lot
How
of
does it
people.
look? Can you tell us?
No, because we haven't looked at any of the Sag A star data. We looked at the EHT data for calibrator sources, and many people in the room are working on that. In fact, we have a review from 4 to 6 on some of the findings that may trickle back to the telescopes, because the telescopes have some problems that have only come to light now that we've analyzed some of the data. So now we have to feed back what we've learned to the telescopes, in addition to having to mitigate the problems with the data set. So it's all complicated, and we're kind of building a bridge as we go. You know, we're jumping off of a cliff and inventing a parachute as we fall. But I'll say two things. One is that a number of the teams in the EHT have come up with methods of imaging data, and we've pitted them against each other in kind of an imaging cage match, you know, to see who can make the best image and how you compare them. And what we found is that you get very, very smart people making these imaging algorithms, and they get slightly different answers. And what that made me think is that there are so many astronomy papers, you know, Avi, you know this, and people who publish an image, and they'll say, I did this with this method. And everyone just believes it. And they say, oh, that looks like the image. That looks pretty much like what the image is going to be. But they don't say, but you can make it this way, or this way, or this way. And they're all slightly different. And what I realize is we don't really have a mechanism for determining which is better or which is closer to the truth. Because you don't know what the truth is.
So don't trust observers is what you're saying.
I'm sure Yogi Berra has the same.
Just make the image a little fuzzy.
Yeah, that's what we do. We just like, you know, every one of our papers comes with a hammer. Like, hit yourself with a hammer, and then look at the paper. And then, you know.
But Shep, we will not let you off the hook so easily, because we want to know if your data. What's the spin of Sag A star? What does your data say? Can you tell us?
Actually, honestly, we have not looked at the Sag A star data yet, because
how
the reason is because we're trying to be very, very careful. This gets back to like something Peter knows.
Okay.
You really want to understand your data pipeline and your analysis methods.
But what about curiosity? I mean, how can you leave the data for months without looking at it when you know that there is something really precious there? You know, like, how can you do that?
Look, VLBI is by definition delayed gratification.
We're used to it.
You know?
I hope we applaud Shep for having self-restraint and not looking at this. Yeah,
I'm just trying to find out if he tells me the truth.
Avi, I've known you for so long. No, I'm a bastard.
The explanation is easy. Radio astronomers are not people; they are robots. They have self-control.
Another country heard from.
I would immediately rush to the data and try to see what it tells us. Okay, you can testify at this time.
What's that?
No, I think it's more complicated than that. I mean, what you have to realize is the data has to be correlated, which is like a production process.
Okay, so it takes time.
So the correlation takes time.
Okay.
And then you end up with these visibility data.
So it's not self-restraint, it's just that the process takes time. That's it.
No, there is self-restraint.
Is it self-restraint?
Yeah, there is self-restraint because the Sag A star and M87 data have been correlated for some time.
Okay.
But I've made the decision, or we collectively made the decision that we have to understand the data on the calibrators first.
I see.
And we have to understand very well the imaging process. And so that's what I'll say about that. And the last thing I would say is that Mislav and I have been working with an animator to make an animated version of the EHT. Really,
That sounds really bad. We've hired a graphic artist to touch up our data, so.
Yeah, really.
When it's being filmed, Shep, and be careful of
Yeah, we're getting airbrushed.
federal agents.
So what we're doing is that can be erased. That's not live stream. It's different. So we've just been working with an animator to tell the EHT story, to describe the physics and some of the things we're looking for. Because there are a bunch of videos out there on YouTube. You can just Google EHT, and people from all over have made these animations. But there's always something wrong with them. Like they don't understand how VLDI works or something. So we hired an animator to tell the story, and we've been working very closely with them to make sure they get it all right. And I think we have a rough cut of that now. So hopefully maybe we'll show it at one of these.
That'd be nice.
Maybe the next,
Will you put it on YouTube or?
Oh yeah.
Okay.
Everywhere.
Then we should link it today.
Well, we're doing this with the Weinstein Company.
Well, now there are so many stories out. Like every day there are a few. I mean, if you look at the New York Times, it's becoming widespread exposure of a lot of very famous people. Actually, I don't know if you're following.
famous.
Yeah, not this project. Not this.
We don't
Let's
want
not
this
go
in
there,
the
shall we?
PHI, yeah. But just watch the news. Anyway.
So I'm Maciek, and I'm one of those people who are inventing parachutes while falling down from the cliff. I spent last couple of months mostly digging into the EHT data. So I can, from first hand, tell you that we really don't have Sagittarius A-star data. If I would have this data, I would have to struggle a little more not to look into it. So I'm looking into our sources. So we don't have Sagittarius, we don't have M87, we don't have South Pole Telescope. But still we have thousands of measurements, thousands of measurements, and I'm doing mostly the quality control, meaning I'm checking whether the statistical model of the data that we assume, whether the data is consistent with that model. More than that, we have two different pipelines to the post-processing, from the correlator to the fringe fitting and the finer tuning of phase fitting. And we are checking the consistency of that, and this is what I've been doing for last about 2 weeks, constructing codes to be able to process these thousands of scans in reasonably short time. So this is very technical and maybe a little more closer to doing something scientific, not that data science is not a science. I'm working on methods to extract periodicity and variability from the EHT data. So we are constructing bunch of different operators. We are testing a bunch of different methods that should be able to tell us whether there is periodicity, whether there is variability, with what certainty. And we're basically developing the tools, and we're testing them against modeled data before we can jump into looking at real data with those tools.
And of course, it's not just periods, but also quasi-periods, quasi-QPOs.
Yeah. So yeah, that's well, it's a complicated definition. What is periodicity? What is variability? And I only learned the difference recently. So QPOs would be variable, not periodic.
Peter.
My research is in an area of mathematical logic and set theory that does not have, and probably never will have, applications to black holes. So I don't have any research report. But I'm in the learning phase, and I've been participating in this philosophy reading group. And the main thing I'm grappling with is trying to understand the proofs of the various singularity theorems.
How do you find the group discussions?
Oh, it's great. Yeah. It's pretty much a mathematics reading group so far.
So it's not, you define more as closer to mathematics than philosophy. What's the distinction?
So
between-
far, the reading group has been, we figured we should focus on understanding the singularity theorems, the various senses of singularity, and looking at the conditions of the theorems before we, raise the philosophical questions about them.
Interesting.
Well, I'm working with Andy and Stephen Hawking and my student Sag A on various aspects of the information paradox. Our current project is precisely as Andy described, so I think I'll just leave it at that.
You mean finding this number?
Yes, finding this number. It's not so easy.
But it's well defined.
It is definitely well defined. I can write down a formula which would output a number for you if you are able to do the calculation.
That sounds like a challenge.
It is.
So maybe we should put a price on it and the young people will find it.
Is it something you can write on a blackboard and then maybe the janitor will come and do it?
Only the blackboard should do that.
Just like Ramanujan story, yeah. I mean, we can have a challenge, like the BHI can fund the prize for whoever solves this. Why not? Andy, think about it. We can put some money into it.
You can outsource this.
It will be somewhat embarrassing if if the janitor were to solve it.
Would you rather have a solution or your product? I mean, that's what's your preference, to have your pride preserved or having a solution? What's your priority?
His pride, of course.
No.
He's got lots of solutions.
I'm in favour of having a prize because it's a chance we'll win it ourselves.
Oh, that's right. That's an important.
Oh.
Now you don't.
The price is 1 month of Andy's salary. So you'll get half of his salary.
Ramesh, it's not a zero-sum game. We have some money. In the
We
pot.
do?
Yeah, we do. We should, but tell us how much it's worth, and then we will put out the price for it.
Well, it of course depends what answer they get.
You get paid more if you get the right answer.
This is an inconvenient
Wrong
truth.
answer is somewhat less valuable.
When the police puts out the prize money for finding a criminal, it's never dependent on the identity of the criminal.
Yeah, but it does depend on whether you catch them dead or alive.
Dead or alive.
So are you saying
I don't think that's true.
the number can be dead or alive somehow?
I don't think that's true at all. I mean, it doesn't matter. I mean, as long as you provide tips that lead to some sort of conclusion, arrest, then you get the money.
Can't you compute this numerically for some set of parameters that might be interesting to judge
Wait
just how
until we
interesting
put the
it
money
is?
and then you.
I'm just asking a question. You're saying you don't know how interesting the result will be. Can't you just solve these equations numerically and for the purpose of seeing how interesting the actual numerical values you get are?
Well, I mean, seriously, it is the kind of calculation we thought we would be able to do in 3 or 4 days.
That's
And,
not an answer to the question.
one could try to evaluate it numerically. We have had the illusion for 3 months now that we're only 3 or 4 days away.
Well, the plasma physics community also had that for several decades.
I think LIGO also felt they were just on the verge for many years too. And they succeeded, so they'll succeed, but it might take longer than you think.
40 years.
In fusion, the solution is always 10 years.
I mean, we could write the formula. You could write the formula on the board. No.
Oh, do you want to write
See
it
if the
now?
janitor solves it. It's pretty short. Oh no, but to define everything that would take.
Okay, so maybe next time we have such a discussion.
But by then they would have solved the problem. If it is still 3-4 days off,
okay,
you should at least pose the problem for somebody else.
Okay, put some pressure on it.
Okay,
That's good.
good.
So do you want to, I mean, we can do it after we finish this, or
No.
right
The
now?
next time we have one of
Oh, the next time. Okay, and we'll decide about the price as well by then.
So now you just solved it.
I'm Chiron.
And over the summer, I worked on dynamical modeling to study whether or not the scenario that all the dark matter is in primordial black hole can be true. In particular, with the first detection of the black hole merger, this idea that dark matter is entirely consisting of primordial black holes has resurfaced. And it turns out that with these small galaxies, there's actually very strict constraints from dynamical effects of these black holes, specifically that the close encounters between, let's say, a 30 solar mass black hole and one solar mass star will actually exchange the energy very efficiently, so the whole system is quite collisional. So this idea here has been studied by Tim Brandt and also by Avi. So we decided to approach that instead of working with analytical solutions, we used a 1D Fokker blank code to investigate this whole scenario. And it turns out that we have mainly we have two findings. First is that for 5 ultra-faint dwarf galaxies that we selected for our sample, there must be some form of dark matter. And in particular, the central dark matter mass density is between 1 to 2 solar mass per cubic parsec. And second, with this form of dark matter, we cannot have primordial black holes with more massive, like 15 solar masses. But that is somewhat subject to how you use the dark matter density profile there. So it's somewhere between 10 and 15. Overall, the idea that the entire dark matter is consisting black holes with 30 solar masses is very unlikely. So, yeah. So that is pretty much all the project. Yes.
Hi everybody, I'm Idan, for those of you who don't know me. So I recently started working with, I've been working with Avi for many years, and him, myself, and Sonic Bose, who's a ITC fellow, started working on an exciting dynamical project looking at stars, dynamics basically of stars around the black hole at the LMC as well as the Milky Way. Now some of you are probably thinking, does the LMC have a black hole? Well, that's one of the aspects we're trying to explore. So that's, we really recently just started that, so there's going to be a little while.
You know, people may not know what the LMC is.
Oh, sorry.
Raise your hand if you don't know what the LMC is.
So it's the Large Magellanic Cloud. It's basically the nearest galaxy to the Milky Way. It's a dwarf galaxy, basically, and it may or may not have a supermassive black hole like the Milky Way does. So that's one of the things we're going to be exploring. Thanks for that, Shep. And on more recent news is we just actually got myself, Giacomo Fragione, who's a postdoc at Hebrew University right now, and Bensei, who is a postdoc here. We just got a referee report back today. It was very positive, and this was on intermediate mass black hole and stellar mass black hole spirals and globular clusters. So we did a long study and basically determined that if you have an intermediate mass, and this isn't actually necessarily new, but some of our results were new. If you have an intermediate mass black hole, it could be say 100 solar mass in a globular cluster around the Milky Way, because of mergers, gravitational waves can you have a merger between a small IMBH and a stellar mass. It can actually eject the merger remnant. There's a kick velocity. You can eject it out of the globular cluster. But if you have a more massive IMBH, say a black hole that's a few thousand solar mass, it's more likely to be retained in the globular clusters. So we did a long analysis of that, and we determined that some of the gravitational wave background should come from globular clusters in our own Milky Way, and maybe I'll give a talk at some point about that. That's so again, we just got the referee report today. It's very positive. We're gonna do a few changes, and hopefully it'll be accepted soon. Hopefully that made sense.
You forgot to mention the possibility that S2, which is one of the stars, of being binary itself.
That's another paper that Avi, myself, Ganji, and Smadar Nuaz, who's at UCLA, have been working on. We've been also looking at S2, not G2, S2, the star which gets to 0.015 arc seconds from Sag A, we're considering whether or not that could be a binary system, because due to Kozai mechanism, I don't know if people know what the Kozai mechanism is, but it can basically can cause a binary to merge, but you also have gravitational GR effects, and GR effects can actually suppress the Kozai mechanism, which is really a very interesting thing. So that's another project we've been working on, and we'll get a few papers from that. It's really exciting stuff, and I definitely would be happy to speak to people about that and get feedback.
Hi, my name is Atish. I'm a postdoc with the Event Horizon Telescope. Most recently, I've been working on this problem of extracting features from the EHT observations, the time domain features. It's an interesting problem, but it's also tricky. It's been tricky by two major effects. One is the scattering and other effects which are adding noise to the data. They sort of wash out the features. Like if there is a periodicity, it becomes hard after the scattering to detect. And the other problem, which is making it tricky, is that when I'm doing these experiments, I'm doing simulations, and I have the luxury of knowing what the period is. When I actually have the observations, I don't have that luxury. So I need to figure out how do I put confidence on what I'm detecting. So that's what I'm working on.
That's very challenging.
Yes.
Oh, okay, so I'm kind of an interloper here.
Well, you shouldn't apologize.
I come and sit in on these roundtable discussions of black hole theory. I actually do instrumentation for the sublimit array, which is one of the EHT stations, and also for the EHT, and find an aspect of the work that people here might be interested in. We're presently expanding the bandwidth of the EHT, doubling it again. So we measure bandwidth in gigahertz or gigabits per second. Let's just talk about gigahertz. We're going from 8 gigahertz of recorded bandwidth to 16 gigahertz of recorded bandwidth. And what's interesting, I think, potentially to people here, the way that we're doing that by recording not just the upper sideband of the received signal, but also the lower sideband. The way in which the receivers work at submillimeter telescopes typically is there's sort of a center frequency that you tune to, and then there's a gap of about 4 gigahertz. We're up at 230 gigahertz. And then there's 4 gigahertz of bandwidth in the positive direction, and then there's the same in the low direction, 4 gigahertz of bandwidth, 4 gigahertz gap, and then the 4 gigahertz of bandwidth. So like an impulse in the middle and 2 bands of received energy. What's interesting about this is that between the high edge of the upper sideband and the low edge of the lower sideband, there's 16 gigahertz of bandwidth. I think Rudy mentioned magnetic fields, and we're doing a full polarization observation, so this raises the possibility of looking at how the polarization angle varies across, instead of just a 4 gigahertz band, which is what we had in 2017, we now have a 16 gigahertz frequency baseline, if you will, across which to measure Faraday rotation on event horizon scales, and in so doing, perhaps yield some insight into magnetic fields that we didn't have before. So that's my instrumentation-related remark.
Thank you.
How the data might improve.
We have you as the last person. Can you introduce yourself?
My name is David James. I'm the new project manager for the EHT, working under Shep. I know
With Shep, not under Shep.
Yeah, okay. With Shep. I'm not a radio expert, so this is all very interesting. I know very few words, so learning from the steep. My background is in optical infrared observations of beyond stellar clusters to work out stellar evolution theory. So from 1-2 million years up to way to the sun.
So as a project manager, what is your role in the project? What are you supposed to deliver? Are you to organize the different components, or
well, so
different groups of people?
There are many working groups. There are many instrumentation needs. There are many proposal requirements, many funding issues.
So you will coordinate that?
Yeah. So I think I'm supposed to be the spider's web in all the various little fingers that are around the tree, and so I'm supposed to bring them all and bring them to the middle, and then report to the the agency, and the people at Chef, and the people at the observatories, so they don't have to figure out all the intricacies themselves. They have all that information centralized and homogenized.
So in the past, Shep lost a lot of hair trying to do it himself, but I guess now he has some help.
Hoping to grow hair back.
Black holes have no hair.
Yeah, we all start to resemble what we study.
It's a big collaboration. How many people are involved in the EHT right now?
Sort of like our dogs and pets.
190 across the world. It's a lot. So on all the papers in the future there will be 190 names. I mean, it's a factor of 10 less than the LIGO collaboration.
Still, a lot of bang for your buck when you think about it.
Well, but then getting the consent from everyone that what is included is agreed upon.
Yeah,
it takes some effort.
Yeah, it's hard. We had to talk about that today, actually. We had a science council meeting, and one of the things we discussed was how you achieve consensus across this broad collaboration on the results that you're going to roll out.
And also what people are allowed to write about it. Which for LIGO was a enormous issue. I mean, members of the collaboration, are they allowed to write papers on their own?
It's a big issue.
It's a big issue. Good luck. We look forward to the first press release, and I guess Shep doesn't know what will be in it as of yet. But,
He didn't tell you he didn't do it, he just is not admitting to it. So
Well, no, I think Maciek confirmed my story.
That's right. Well, thank you all for coming, and happy Thanksgiving to everyone.
Yes.
And see you next week.
By the way, I think we'll be in here to go through the review.
Yeah, we're going to set up the meeting in here.
Okay, good. Yeah, I think the camera now works. So,
Oh, great.
Thank you.
We have a USB, so we can.